Hey everyone, get ready, because today we are doing a deep dive into fluorine.
Ooh, exciting.
Yeah, it is. It's an element with well, a bit of an interesting reputation. It's known for being both a hero and a villain.
Yeah, that's a great way to put it, actually. I mean, fluorine, it's incredibly common. You probably, interact with it every single day.
Right.
But it's also, insanely reactive.
You're telling me we've got some seriously cool info on fluorine for everyone today. We're going to break down why it's so reactive and all the surprising ways we use it.
Right, like nuclear energy.
Yeah. And even nonstick pans.
What?
Yeah.
Wild.
But of course, we're also going to have to touch on its, how do I put this? Less glamorous side. But first, I think we need to really unpack just how reactive this element really is.
Oh, yeah, for sure.
So the sources you shared really emphasize how fluorine reacts with almost everything.
It does.
Even things that we usually think of as being totally inert.
Yeah, totally.
Everything, really.
Yeah, pretty much.
Can you give me some examples? I'm having a little trouble picturing this.
Okay, so think powdered steel,
Oh,
glass,
okay.
asbestos.
Oh, wow.
It can even make wood and water spontaneously combust.
No way.
Yeah.
That's insane. Okay, this is not what I would call a subtle element. It's like the Tasmanian devil of the periodic table, just absolutely wild reactivity.
That is, you know what? That's actually a really good analogy.
Right.
But there's a reason for all this craziness.
Yeah.
It really all comes down to its electron configuration and its super high electronegativity.
Okay, confession time. Chemistry is not my forte. Can you maybe break those terms down for me and for our listeners who might not be chemistry whizzes either?
Yeah, of course. So imagine fluorine is like playing a super, super competitive game of tag. And the goal is to grab an electron to complete its outer shell.
Okay.
So that's essentially what electronegativity is. It's just like how strongly an atom attracts electrons. And trust me, fluorine plays to win.
So it's that friend who always has to be the center of attention at a party.
Yes, exactly. Always. And that's exactly why it took scientists so long to finally isolate it.
Yeah. Can you imagine what those early chemists were thinking as they get closer and closer to isolating something so reactive, so potentially dangerous?
I can't even imagine.
Talk about a challenge.
It's wild. The amount of dedication and, frankly, risk involved in early chemistry. It's amazing.
They don't make them like they used to, huh? It took over 70 years. And sadly, several unfortunate incidents before fluorine was finally isolated.
Wow.
Henri Moissan definitely earned that Nobel Prize in 1886.
Absolutely. Monumental achievement. Like you said, the dedication and perseverance of those early scientists is just incredible.
It's pretty wild to think about, those early discoveries. I'm sure those chemists weren't just isolating fluorine for the thrill of it.
Oh, absolutely not.
What sort of applications came from being able to do that?
So many. Isolating fluorine opened up so many doors.
Like what?
Well, for one thing, it's a key player in the nuclear industry.
Hold on, nuclear, as in power plants and other things.
Exactly. See, during the Manhattan Project, they needed a way to enrich uranium to make the atomic bomb, obviously.
Okay.
And that meant they had to isolate uranium-235
right
from a mix of different uranium isotopes. You know?
Okay.
And guess what the key to doing that was?
I'm going to guess fluorine.
Fluorine. You got it.
Of course.
So, uranium hexafluoride, that's what they're called, these compounds of uranium and fluorine,
right?
They basically become a gas at, pretty low temperatures.
Really?
Yeah, and that was super important for this process called gaseous diffusion.
What is that?
It's how they separated the different uranium isotopes. They did it by weight.
Wild.
Yeah, so basically by bonding fluorine with uranium,
Yeah.
it was like they could make a gas that let them, separate out the exact kind of uranium they needed for the bomb.
Wow. That's incredible. And a little bit scary, to be honest.
Yeah, just a little bit.
But I'm guessing that's not the only place we find fluorine being used, is it?
Oh, not even close. You probably have some in your kitchen right now.
Okay, now you're freaking me out. You're not saying I have a stash of enriched uranium in my pantry, are you?
No, not quite. Think about your nonstick cookware.
Okay.
Ever heard of Teflon?
Duh. It's the only way my omelets don't stick to the pan.
Well, that super slippery surface is all thanks to fluorine.
Get out.
Yeah. It's a fluorocarbon polymer called polytetrafluoroethylene. PTFE for short.
No way.
Wow.
So you're telling me the same element that can basically make wood spontaneously combust is also what makes my breakfast so perfect?
Pretty much.
That's incredible. Please tell me there's more, because this is blowing my mind.
There's more. Fluorine is also how we get refrigerants to keep our food cold
Oh, wow.
and our homes comfortable, all that.
Okay, so nuclear applications, nonstick pans, fridges. Is there anything fluorine can't do?
Well, it's not exactly a miracle worker. Like most things in life, there are two sides to every story.
Okay,
Fluorine might be versatile, but it's also got a bit of a dark side.
dock side. We can't just leave it at that. What are we talking about here?
Well, remember those refrigerants we were talking about before?
Yeah.
Turns out some of them, those older ones, the CFCs,
Yeah.
like really bad for the ozone layer.
CFCs. Okay, yeah. That does sound kind of familiar. I think I learned about those in school.
Yeah.
Weren't they, like, really bad news, environmentally speaking?
They were big time. They were at everything, fridges, aerosol sprays,
Oh,
and it turns out super damaging to the ozone layer. And that's a big deal, right?
Yeah.
Protects us from all that UV radiation.
right. Yeah, of course. So what happened? Did we just keep using them?
Actually, no, this is a great example of how, like, global cooperation can actually work.
Oh, good.
Yeah. So in 1987, all these countries got together, signed the Montreal Protocol, and basically phased out CFCs.
Oh, wow. Okay. Glad we dodged that bullet. So, problem solved, right? No more evil fluorine to worry about.
Well, not so fast. Turns out the replacements, some of them at least, like the HFCs,
Yeah.
they came with their own issues. So they might not have messed with the ozone layer as much,
Okay.
but they were potent greenhouse gases.
Oh, no. Are you serious? So we basically just traded one environmental problem for another. Talk about unintended consequences. So fluorine is secretly contributing to climate change.
Kind of, yeah. And it's not just those refrigerants either. There's also sulfur hexafluoride.
What's that?
It's a gas used in some high voltage equipment.
Yeah.
And that stuff,
Mm.
that is considered one of the most potent greenhouse gases we know of. Like thousands of times worse for global warming than carbon dioxide.
Oh, man. Okay. That is definitely something to be concerned about. Ozone depletion, greenhouse gases, anything else?
Well, we can't forget fluorine and a lot of its compounds are straight up toxic.
Right, that makes sense. Like those early chemists we were talking about.
Yeah.
They weren't kidding around. But what about fluoride in toothpaste and stuff? Aren't we
Yeah.
always told that's good for your teeth?
Yeah, it's a bit of a tricky one. Because, yeah, small doses of fluoride are good for your teeth.
Mm.
But too much can cause all sorts of issues like skeletal fluorosis, which basically affects your bones.
Yeah.
It's all about balance, really.
The dose makes the poison.
Exactly.
Yeah.
It really just shows how important it is to, like, really understand the elements that we interact with, right? And even stuff that seems simple can actually have these really complex implications.
Absolutely. Well, there you have it. Fluorine, reactive, versatile, a total game changer in history, and maybe a little bit of a troublemaker.
Oh, yeah. And if your sources are any indication, we're not done learning about it either. There's still so much to uncover, about its uses and impact and all that.
It really makes you wonder what else is out there? What other seemingly ordinary elements are hiding these incredible secrets, just waiting to be discovered? That's something to think about, isn't it? If this deep dive has sparked your curiosity, why stop here? Do some of your own research to see what you can find. You might be surprised at what you uncover. Until next time, stay curious.